Hello, ladies and gentlemen. Now I'm going to teach you oscillations in 30 minutes. It's going to be difficult to keep up, so feel free to pause at any time, okay, to take notes or to digest the information in this video. And also, it's going to be it's a marathon to watch this video. So I'm going to thank you in advance if you can make it through these 30 minutes. Now, let's start with a very basic oscillation. Over here is a spring and a mass. Okay, so this is a spring and it's attached to a mass. Now the center point of this oscillation is called the equilibrium position. And the equilibrium position is where the mass will remain if you just stay still. So the mass is going to go up and it's going to go down. So it goes all the way up to here and it goes all the way down to here. This maximum distance here, this is called the amplitude. Now the amplitude of the oscillation is given a value x0. So this thing is going to go up and down, up and down, up and down, up and down, up and down. Now if we drag out this motion in time, okay, this is what we're going to get. This is called the displacement with time graph. Okay, so this is going to be time, and then the top is going to be displacement. Okay, so this is going to be called the displacement. Now displacement is given a variable x, and the time is given a variable t. So in this case, we started the stopwatch when time t equals to 0. We started the stopwatch when the mass was halfway and going upwards. But what if we started the stopwatch later? Now, if we start the stopwatch later, okay, let's say we wait until the mass is all the way at the top, then we start the stopwatch. Then this will be our new start time. And as you can see, if we start the watch here, we get a sine graph. But if we start the watch here, we get a cosine graph. Now, can you think of other places that you can start the stopwatch to get different kinds of graphs? What happens if we start the stopwatch over here? If we start our stopwatch over here, then this will become a negative sine graph. So here's the first thing about oscillations. Now, the first thing about oscillations is that when you start the stopwatch, okay, will determine what kind of graph you get. Okay, so whether you get a sine graph, a cosine graph, a negative sine graph, a negative cosine graph, you could start the stopwatch over here, t equals to 0, then you get a negative cosine graph, minus cos. Or you can start the stopwatch anywhere in between, like some random place here, and then you get a graph that isn't a sine or a cosine, but something plus, a phase shift. Okay, so the first thing you need to know about oscillations is that when you start the stopwatch, that's going to determine what kind of graph you get. Now, let's not be too crazy. Okay, let's start the stopwatch at the middle. Okay, so here's a mass. It goes up 3 cm, and then it goes down 3 cm. So what kind of displacement graph are we going to get? Let's do a very simple displacement graph with nothing too fancy, okay? So we're going to just do a simple sine graph, okay, and this is what it's going to look like. Now, so this is two oscillations. One complete oscillation is when it goes up, all the way, back down, and then up again. When it reaches its original position again, and it's going upwards, that's considered one complete oscillation. Now, in terms of the axis, we can say that the amplitudes of the motion are 3 cm. So this will be 3 and minus 3 respectively. Now, what about the period of the motion? Let's say we give this period 5 seconds. 5 seconds. So what we have is some information over here. x0, the amplitude will be equals to 3 cm. The period will be equals to, let's say, 5 seconds. All right, 5 seconds. In this case, we know the middle point here will be 2.5 seconds. All right, so this is 2.5 seconds. Now, let me ask you a simple question. And the question will be as follows. What is the displacement at 1.25 seconds? What is the displacement at 1.25 seconds? Well, it's very easy. 1.25 seconds is somewhere here in the middle. So the displacement at 1.25 seconds, the answer will be 3 cm. 3 cm. The answer will be 3 cm. Easy, right? But what if I ask you something weirder? So what is the displacement at 0.85 seconds? So 0.85 seconds is somewhere over here. So we know the displacement is between 0 and 3. So this is the time that we want, t. Okay, we want this displacement. So it's like, what on earth is the value of x? Now, how are we going to find the displacement at 0.85 seconds? Not to worry, let's figure it out. Now, first of all, okay, we're going to compare this sine graph. This is the graph that we had just now. This is 3 cm. Okay, this is x and this is t. And over here is 5 seconds. Now we're going to compare this with a normal sine graph. A normal sine graph would be something like y and theta. Okay, y and theta. So this is a normal sine graph. And you know that theta over here is 360 degrees. And this amplitude here, let's say, is 3 cm as well. Are you able to write the formula for this sine graph on the right? I'll be able to write it as y is equals to a sine theta. Wouldn't you agree? All right, that's how you would find y equals to a sine theta. Now, what about this graph on the left? You get x is equals to 3 sine, but then, of course, you got something weird inside. Because you see, what goes into a sine function is an angle. You can only put angle inside here, like let's say 45 degrees, 60 degrees, 120 degrees, or something like that. You can't put a time. But on this axis is a time. So how are we going to put a time inside the sine function? Because you can't put sine 5 seconds. That doesn't make any sense whatsoever. So our first job is that we now have to convert the time into the equivalent angle. Now we want to know what is the displacement at 0.85 seconds. So how do we do this conversion? All right, so now let's take a look. 0.85 seconds is equals to what angle theta? But we do know that, look at this, 5 seconds here is equivalent to 360 degrees. So 5 seconds is equivalent to 360 degrees. So if 5 seconds is 360 degrees, then what about 0.85 seconds? What is it equal to? Now, how can we do this? Then do this very easily by using abracadabra. Okay, so we divide both equations, okay, and then we get this thing. So we get 360 degrees multiplied by 0.85 over 5 will be equals to theta. So this is great. So now instead of the time, what time do we put in here? We can put in the value 0.85 divided by 5 times 360 degrees. Now, scientists don't work in degrees, scientists work in radians. So you get, instead of 360 degrees, we write 0.85 divided by 5 multiplied by 2 pi. Now let's throw that into a calculator, and we'll get something like x is equals to 2.63 cm. Well, that's exactly what we expected. It's somewhere between 0 cm and 3 cm. So now what have we found? We have found a way, okay, to write down the displacement of the oscillation in sines and cosines. Wow, okay, so now we have learned a skill. Skill number 1, we are able to write down the function of the displacement with time graph, okay, at a glance. Okay, so I'm going to test you, right, whether you can write the function of the displacement with time graph at a glance. Okay, this is the graph that we have just written before, we have just done before. Okay, this is exactly the same graph that we have done before. This is just now, do you remember the values? Okay, the values of the displacement is, amplitude is 3 and minus 3, and the period is 5 seconds, okay, in terms of cm. So we write down x is equals to 3 sine. Okay, now I want to find the displacement at a particular time t. So do you remember how we convert the time t into an equivalent angle? That's right. We take t divided by 5. Then we multiply it by 360 degrees or 2 pi. All right, so this is the function that we got. Okay, it's exactly what we did just now. All right, so we have learned a skill number 1. We are able to write down the function of the displacement with time graph at a single glance. Okay, now I would like to do that again, but this time instead of numbers, I'm going to give you just alphabets. Follow me, okay? If you follow through this entire lecture, I promise you, simple harmonic motion will be very, very easy. Okay, So now I'll write down. Now, can you write down this function of this displacement at a glance? Very easy. X is equals to x naught sine t over t multiplied by 2 pi. Now, what we also like to do is that we like to rearrange this thing. We're going to rearrange this thing, okay, to get x equals to x naught sine. Instead of putting the t over big T, we'll put 2 pi over t multiplied by small t. Okay, so we rearrange it into this fashion. Now, do you notice something? 2 pi over t. When have you seen it before? That's right, circular motion. 2 pi over t is called omega. Only in this case, it's called the angular frequency of the oscillation. Now, what is angular frequency? It is a conversion factor. It converts time into angle. So if you want to find out what is 0.85 seconds in terms of what angle, so all you got to do is take 0.85 divided by the 5 seconds, and then you multiply it by 2 pi. So basically 2 pi divided by 5 times 0.85 seconds gives you the angle, right? So omega is the conversion factor that converts time into angle for simple harmonic motion. So in general, this is the equation for a simple harmonic motion. Okay, so this first part of the lecture is about how you're going to write down the function of the displacement with time of a simple harmonic oscillation at a single glance. All right, so why don't I test you, okay, on the next few functions over here. Here is x and here is t, okay, and this is a cosine graph like that. Okay, this is 5 and this is minus 5. Over here, this function is 3. And over here, this time over here is 6. And over here, this time here is 9. Are you able to write the function of this graph at a single glance? It's very easy. X is equals to 5 cosine 2 pi divided by something multiplied by time. Okay, and what is divided by what? Divided by the full cycle. The full cycle of a cosine graph starts from here and ends with here, so it's 6. So it's 2 pi over 6. Okay, don't simplify any further. That's about as much as we can go. All right, now let's begin on the next part, okay, of our simple harmonic motion or oscillation. Skills number 2. Skills number 2 is to derive the velocity and acceleration with time from the displacement graph. Okay, so let's take a look at our simple displacement time graph over here. Here is x and here is t. This is a sine graph, okay, so we're going to put down x0. Remember, x0 means amplitude, minus x0, and t means period. And we want to find out what is the displacement at any time t over here. So we have x is equals to x naught sine omega t. This is your displacement time graph. Next, how do we obtain velocity? Now, we do know that velocity is the rate of change of displacement. So that means that velocity is dx dt. So let's differentiate this. For those of you who don't remember how to differentiate velocity, now first of all, the outside coefficient remains the same. The sign changes into a cosine, and the inside is then differentiated again to take out the omega. So now the velocity will be x naught omega cosine omega t. If we sketch the graph, this is a omega graph. This is a cosine graph. So the cosine function will look like this. Okay, this is a cosine function. Now please note that the period remains the same because the frequency hasn't changed. Only the shape of the graph has changed. But let's take a look at the coefficient. Now, if I give you the formula y equals to AB cosine theta, and then I told you to find the maximum value of y, you will say the maximum value of y is AB, wouldn't you? So over here, the maximum value of the velocity will be x naught omega. And over here is negative x naught omega. So we can easily write down the maximum speed of the oscillation is x naught omega. All right. Now, how do we obtain the acceleration from velocity? If you said this differentiation, you are correct. So A is equals to the differential of the v dt. And let's differentiate v again. So so those of you who don't remember how to do differentiation, I'll do it with you. So first of all, we preserve whatever is in front. So that's x naught omega. The cosine becomes a negative sign. Becomes a negative sign. And then we take the omega t, the omega goes out again, so this one becomes omega squared. So altogether we have A is equals to x naught omega squared minus sine omega t. Let's rearrange this formula a little bit because it looks super ugly. So we're going to put down A equals to minus omega squared x naught sine omega t. So if we draw the acceleration graph with time, we were going to get a negative sine graph. Okay, so this is going to be a negative sine graph, and the period remains the same at t. But what about the maximum and minimum values? Well, the maximum and minimum values are given by the coefficient, which means that this will be omega squared x naught and negative omega squared x naught over here. So the maximum acceleration will be equals to omega squared x naught. Now, I want you to look very carefully, all right, at this part of the equation. This part of the equation is x naught sine omega t. Have we seen it before? Yes, we have. X naught sine omega t is displacement. So we can also simplify this equation to be A is equals to minus omega squared x. Wow, what does this mean? Now remember that acceleration is the second derivative of the displacement with time. So that means to say is the differentiate displacement twice. Okay, so what this means is that if this is the most important equation in simple harmonic motion, this is called the defining equation. The defining equation of SHM. Now, what does this defining equation mean? It means that the definition of simple harmonic motion, okay, is as follows. The definition of simple harmonic motion is any motion where the acceleration of the body is proportional to the displacement from the equilibrium position, but in the opposite direction. And it is exactly this formula that is the definition of simple harmonic motion, where the acceleration of the body is proportional to the displacement from the equilibrium position, but in the opposite direction. So how do we know that it's the opposite direction? Because of the negative sign. Now, what does this equation mean? This equation means that it's a motion where if you differentiate the displacement twice, you get the acceleration, which is the same function. You get the same function, but opposite direction, but negative. Now, so what does this mean? Now, can you think of any functions that you can differentiate twice to get the same function? Why don't we try x cubed? When we differentiate x cubed twice, we will get 6x. So it's not the same function. All right? Not the same function. What about, we can differentiate an exponential function twice and get same function, similar function, but negative. But really, the function that you can differentiate twice and get the same function, but negative, is a sine or cosine function. So what this means is that the defining equation of SHM tells us that it is composed of a sine function. Sine function, right? That if you differentiate the sine function twice, you'll get the same function, but in a negative direction. Okay? So that's it for simple harmonic motion for the first part. We are now able to derive the velocity and acceleration with time from the displacement time graph. Now let's move on to the second part of simple harmonic motion, and we're going to talk about energy. So we're going to talk about the energy, which is skills 3, okay, which is to derive the energy of the SHM at any point. Derive the energy of the SHM at any point. Now let's take a look at how a pendulum oscillates. Okay, so this is how the pendulum oscillates. Over here, it's kind of like moving fast in the middle, and then it stops in the mid, and then it goes this way. So it's fast again, and then it stops. So over here, when it stops, the KE will be equals to 0. So on both sides, the KE equals to 0. And in the middle, the KE is fast. So the KE is equals to 10, let's say, which is 10, which is the maximum. All right, so in the middle, however, you notice that the middle point is when the GPE is lowest. GPE is the lowest. So we write down the GPE here. Let's say the GPE is 0. Now, if KE is 10 at the bottom, and then GPE is 0, then what would the GPE be at the side? The GPE must be 10, right? The GPE is equals to 10. Now, we define a new kind of energy called total energy. Total energy will be KE plus GPE, which is 10. So over here, we realize that total energy is also 10. And over here, we realize that total energy is also 10. Now, okay, so let's take a look at how we can draw the graph of the SHM, okay, in terms of energy. So now we're going to draw a graph, okay, of energy against time, energy against position. So let's take a look at this graph. Now over here, this is energy against the displacement. So on the left-hand side, the ball goes all the way to the left. So this is minus x0, the ball goes all the way here. Then on the right, the ball goes all the way here. So we put this as x0. Now, so we're going to draw the KE first. At this point, the KE is 0. KE is 0. At this point, the KE is also 0. KE is also 0. But in the center point, the KE is maximum. So that's the KE at the top. Now, I don't think it's going to be a triangular function, so it's probably a curve. Let's draw a curve for now. So this is the KE graph. Okay, it's fastest in the middle and it's slowest at the ends. Next, we're going to draw the potential energy graph. Now over here, the GPE is 10. So the GPE is 10, or maybe a bit lower. Over here, the GPE is 10 as well. GPE is 10. And in the middle, the GPE is 0. So this is the GPE graph. Okay, so this is the GPE graph. Next, we're going to draw the total energy graph. The total energy is 10, 10, 10. So it's 10, 10, 10. So the total energy must be a straight line. Okay, so this is the total energy graph. So this is what I like to call the energy with displacement graph. All right, as you can see, it's made of 3 graphs, 1, 2, and 3. So I like to call them the smiley face graph. The smiley face graph is the PE graph because PE makes me happy. Okay, PE makes me happy. And then the frowny face graph, if PE makes me happy, then KE makes me sad. Okay, and then the last one is TE. The TE makes me glad. TE is like blah. Okay, so you can remember the 3 graphs as follows. PE makes me happy, KE makes me sad, and TE is blah. All right, so what is the maximum and minimum values though? Okay, so you notice one thing over here, that the maximum KE is 10. So max KE is 10. The maximum PE is also 10. And then the total energy is also 10. So is there an equation which allows us to find the KE, PE, and TE? Well, I'm glad you asked. There is. Look. So over here, let's take a look at our previous work done. The previous work that we did. The maximum speed of the simple harmonic motion is x naught omega. Now we know that KE is given by the value half mv squared. Okay, half mv squared. So if we substitute the speed inside this equation, so we get the maximum KE is equals to half m this thing squared. So omega squared x naught squared. Wow. So we found the maximum KE immediately already. And since the maximum KE is also the maximum PE, so we can write down that the maximum potential energy of the simple harmonic motion is also half m omega squared x naught squared. Now, where did we get this from? We got this from, remember, x equals x naught sine omega t, and then we differentiated it, and then we got v equals x naught omega cos omega t. And then we got the max speed is x naught omega. So the maximum Ke is half mv squared, and v is x naught omega, so we square that. And the maximum Pe is half m omega squared x naught squared, and the total energy is also half m omega squared x naught squared. So where can we find this point? This point is over here. All right, this point is over here, is half m omega squared x naught squared. Ta-da! Okay, now, so let's take a look at potential energy, okay? The potential energy. Now, remember that potential energy makes me happy. So this is the PE graph, isn't it? Now, does this PE graph remind you of any other graph? E and X. This is PE, right? Now, doesn't it look like a PX squared graph? Does it look like an X squared graph to you? Now, it's an X squared graph where the value of the maximum value when X naught, this is half m omega squared x naught squared. So this means that potential energy, we can make a guess. The potential energy graph is an x squared graph, and it's going to be half m omega squared x squared. And the maximum potential energy when x equals to x naught will be PE max is equals to half m omega squared x naught squared. So now we have the potential energy graph just like that, just by inspection. By inspection, we can see that the potential energy graph is an x squared graph. Okay, so next, now what about the kinetic energy graph? The Ke graph looks like this. Is a frowny face. PE makes me happy, but Ke makes me sad. Okay, so the kinetic energy graph, we know that it's going to be some kind of minus x squared graph plus c, isn't it? We're going to minus x squared graph plus c. But remember that total energy is equals to Ke plus potential energy. So total energy is given by half m omega squared x naught squared. And this is Ke plus Pe, and Pe is given by half m omega squared x squared. So that means that Ke graph will be equals to half m omega squared x naught squared minus half m omega squared x squared, which is cool because it becomes half m omega squared x naught squared minus x squared. And that is where we get the minus x squared plus c. So this will be the minus x squared, and this will be the plus c. So this is now the Ke graph. So let me just summarize, okay? Let me just summarize. Now, the maximum Ke, the maximum Pe, and the total energy graph is given by these values equals to half m omega squared x naught squared. Then the PE graph is given by a smiley face, half m omega squared x squared, which is a smiley face. The Ke graph is given by half m omega squared bracket x naught squared minus x squared. And because it's minus x squared, so it's a frowny face. Okay, so that is the energy with respect to time. So derive the energy of the SHM at any point has been accomplished because we know that the PE graph is half m omega squared x squared. The Ke graph is half m omega squared x naught squared minus x squared, and the total energy graph is half m omega squared x naught squared. So we can derive the energy of the SHM at any point. Okay, now I want to take a look at the Ke graph over here, this Ke graph. Now let's take a look at Ke. We know that Ke is half mv squared. So let's compare this equation, half mv squared, to this ridiculous equation, which is omega squared x naught squared minus x squared. Now, what can you tell me? This means that if these two are Ke, then v squared is equals to omega squared x naught squared minus x squared. So basically, v is equals to plus minus omega square root of x naught squared minus x squared. Wow, this is another formula that we need to know. Okay, now we have come to the end of simple harmonic motion. I promise. Wow, we have absolutely come to the end of simple harmonic motion. But because I know that it is impossible to learn simple harmonic motion in 30 seconds, in 30 minutes, So what I'm going to do is I'm going to give you a super summary of simple harmonic motion. And I'm going to do it right now. You will be surprised how much you already know about simple harmonic motion just by watching this video. Okay? Now, first of all, we start with the displacement time graph, which is x is equals to x naught sine omega t. Do you remember that? Okay, so we'll have x and then we have t. This is a simple sine graph with a t over here and x naught. Next, we get the velocity graph. The velocity graph is obtained by differentiating the displacement graph with the maximum velocity equals to x naught omega. So over here, we'll write down v, this is v, and this is t. Sorry, the sign changes into a cosine, right? So then we draw a cosine graph, all right, and this is t. And the maximum value is given by x naught omega. Then we differentiate it again to get acceleration is minus omega squared x naught sine omega t. And the acceleration graph is basically the displacement graph flipped around. So we get a negative sign, right? Also the same period, but the maximum value is now omega squared x naught. Okay, so this is the three graphs in terms of time. Now, from this graph, from acceleration, we also get minus omega squared x. Okay, now, what about in terms of the displacement? What about velocity with displacement? So we have this equation, v is equals to plus minus omega square root of x naught squared minus x squared. Now this is the graph of an ellipse. Okay, this is the graph of an ellipse. So the velocity with displacement graph looks like a circle. But don't be afraid. I'm going to show you how this graph is obtained. Now over here, remember, this is how the pendulum moves. This is stop. This is fast. This is stop again. Then this is fast. Then this is stop again. Right? So let's see how it looks like on a displacement graph. So the displacement graph, this is x naught. Over here, the ball goes to the left minus x naught. So let's take a look at how it works, okay? Now, on the left-hand side, the velocity is 0. So the velocity is 0. When it goes to the middle, the velocity is fast. Then when it goes to the end, the velocity is 0 again. Now, that doesn't stop there because the pendulum comes back again. So when it goes backwards, remember, when it goes backwards, the velocity is negative velocity. So this is how it works. At the end, the velocity is 0. Then when it goes to the middle, the velocity is fast. When it goes to the end, the velocity is 0 again. And now it's going backwards, so the velocity is negative. And then back to 0 again. And that's how you get the circle, this elliptical thing. Right, the last graph that you need to know, okay, is the displacement and acceleration graph. This is also the defining graph for simple harmonic motion. This is the A and this is the X graph. Okay, now let's take a look at the formula. A is equals to minus omega squared x. This is basically the equation of a straight line. Okay, this is the equation of a straight line with a gradient of minus omega squared. Okay, so here's 5 graphs for simple harmonic motion. Okay, next we're going to talk about the energy, okay, graph. Now on the right hand side, we have the energy with displacement graph. So this is the energy and the displacement graph. Remember, the ball goes from minus x naught to x naught. Okay, now at the ends, okay, we're going to draw the KE first. Remember, KE makes me sad. So the KE graph looks like this because at the ends, the ball is stopped, and then at the middle, the ball is very fast. Now, what about the PE graph? The PE graph is the opposite of the KE graph, okay? The potential energy is 0 in the middle, or the lowest in the middle, and highest at the ends. So PE makes me happy. Now we'll draw the total energy graph, which I kind of like messed it up. Okay, so this is the total energy graph. The total energy graph is a straight line. Okay, the equations for the PE, TE, and KE are as follows. PE is equals to half m omega squared x squared. KE is equals to total energy is equals to half m omega squared x naught squared. Now x naught is a constant, but x is a variable. The last one is kinetic energy is half m omega squared bracket x naught squared minus x squared. That's also how we get the equation V is equals to plus minus omega square root x naught squared minus x squared because of this equation over here. All right, so now that is the equation for the energy with respect to displacement. Now, last but not least, okay, let's talk about energy with respect to time. Energy with time. All right, so let's take a look at how the energy with time graph is derived. Okay, so this is energy. As time passes, what remains constant is the total energy remains constant. TE remains constant. Okay, let's talk about how the KE changes. Okay, let's do the KE first. So the KE over here is 0, then the KE over here is max. Then the KE over here is 0, but then it doesn't stop. It goes back again. KE over here is max, and then the KE over here is 0. That's one complete oscillation. So let's draw it, okay? The KE here is 0, then the KE here is max. Then the KE here is 0, then the KE here is max, then the KE here is 0, and that is one complete oscillation or one period. Now let's draw the graph. It's going to look like this. It's not a McDonald's graph. Instead, it's more like two humps. Okay, that is the KE graph. So this is KE graph. Okay, how about the potential energy graph? The potential energy graph is the exact opposite of the KE graph. The potential energy graph looks like this. Potential energy goes to 0, then potential energy goes to top. Potential energy goes to 0, potential energy goes to top. This is the PE graph. Okay, notice that there are two humps for every period. So this is the KE graph, one period. So it's two humps per period. Okay, what about the PE graph? The PE graph also has two humps per period. See, this is one hump here, half a hump here, and half a hump here. So also two humps per period. Okay, so this actually brings us to the end of simple harmonic motion. I promised simple harmonic motion in 30 minutes, and that is what I delivered. Those of you who need a screenshot, this is the screenshot to grab. So thank you and have a nice day.